Imagine signing a 10 million baht check for a brand new, state-of-the-art CNC machine. The manufacturer guarantees it can produce 1,000 parts a day. But at the end of the month, you check the production logs, and you find it is outputting only 450. When you ask the floor manager what happened, you get qualitative, generalized excuses. The operators took too long to calibrate the machine, or a brief power dip stopped the line for a few minutes yesterday. Modern systems engineering rejects these qualitative buffers. Optimizing a production line requires uncompromising quantitative diagnostics to pinpoint exactly which seconds are draining your investment. OEE, or Overall Equipment Effectiveness, functions as the gold standard metric for isolating the specific coordinates where time and revenue leak out of a production cycle. Effective management treats the factory floor as a continuous, interconnected system where a single unmeasured error in one cell compounds mathematically across the entire chain. Perceived capacity shortages are rarely solved by purchasing new equipment. Instead, growth comes from reclaiming the hidden factory currently trapped inside your existing operations. This time waterfall chart illustrates the mathematical rigor of the OEE formula. It calculates the product of 3 distinct metrics: availability, performance, and quality. Let's assume a machine scores what sounds like an excellent 90% in each individual category. Because these metrics multiply against each other, inefficiencies compound. 0.90 cubed equals 0.729. Even with all departments performing at 90%, the overall effectiveness of your machine drops to 72.9%. World-class manufacturing facilities set their baseline OEE at 85%. Yet, when small and medium enterprises run this diagnostic for the first time, they typically discover their actual OEE sits somewhere between 40 and 60. These microstops and deliberate speed reductions easily evade traditional tracking. A worker with a clipboard will not log 50 separate 10-second delays throughout a shift. The final pillar is quality. This is the ratio of first-pass good parts compared to the total number of parts produced. Quality is compromised by process defects, parts that are warped or off-spec during regular runs, and startup rejects, which are the first batch of parts wasted while the machine reaches thermal stability. What remains is your final fraction of fully productive time. Without applying this rigid mathematical deconstruction, these 6 specific losses will remain permanently camouflaged as standard daily operations. Consider Siam Precision, a factory overwhelmed by automotive orders. To meet demand, management proposes a 5 million baht capital expenditure for a new machine. They are running mandatory weekend overtime and operating under the assumption that their existing equipment has hit a physical capacity ceiling. Before signing the purchase order, they freeze the spending and run a strict 1-week OEE diagnostic on their current line. The audit begins with availability. A standard 480-minute shift is decimated by 30 minutes of random breakdowns and a staggering 90 minutes of setup time. That leaves only 360 minutes of actual runtime. Their availability score is just 75%. Next is performance. The machine is rated to produce 1 part per minute, meaning they should yield 360 parts in the remaining time. However, operators are running the equipment slowly to protect fragile cutting tools, resulting in only 288 parts. This deliberate speed reduction drops their performance score to 80%. Finally, quality. Out of those 288 parts produced, 14 fail to meet specification. The quality score registers at 95%. The final equation reveals the truth. 0.75 times 0.80 times 0.95. The existing machine is operating at an OEE of only 57%. This 43% delta represents the hidden factory, actual production capacity currently lost to process friction that can be recovered without additional capital. The engineering team targets the data. They reduce setup times from 90 minutes to 15 minutes. They upgrade the cutting tools so operators can run at 100% speed, and they install custom jigs to eliminate the defects. Those targeted operational tweaks boost the OEE to 82%. The factory fulfilled the new order volume, eliminated weekend overtime entirely, and saved 5 million baht in unnecessary capital expenditure. OEE is a vulnerable metric. It is only as reliable as the data fed into it, and plant managers frequently manipulate the numbers. Maintaining data integrity requires strict rules. Rule 1. Scheduled breaks or pauses in production due to a lack of orders are defined as planned downtime and must be mathematically excluded from the baseline. Rule 2. Human operators will never reliably log 10-second microstops on a clipboard. Moving toward a smart factory requires integrating IoT sensors to extract data straight from the hardware's logic controllers. Rule 3. Never hide setup and changeover times inside planned downtime to artificially inflate availability scores. Doing so ensures those inefficiencies will never be corrected. Rule 4. If you use OEE as a tool to punish operators for low numbers, they will systematically falsify the data to protect themselves. It is a diagnostic instrument, not a weapon. Rule 5. Do not measure every machine at once. OEE tracking must start on your bottleneck, where a 1% gain in efficiency directly increases the entire factory's throughput. Ultimately, OEE functions as an uncompromising truth serum. It strips away operational illusions, reveals exactly where your time is going, and protects your cash flow from unnecessary capital expenditures. But resolving your machine efficiency introduces a new danger. If you optimize OEE so successfully that you produce faster than your customer actually buys, you create a massive surplus. Next time, we will examine takt time and the lethal financial danger of overproduction.